welcome to the numerical ship and offshore hydrodynamics in this lecture 4. Now, in this lecture we are going to continue from our previous lecture, like some concept of the basic hydrostatics still we are going to discuss. Along with that we are going to discuss the how I calculate the numerically the restoring coefficient, which is we have 3 restoring coefficient that we need to calculate. And also we are going to discuss the brief outline that how we are going to solve the equation of motion, like whatever we do, the finally our main aim to calculate the under the waves, how what is the displacement of the vessel, right. So, at the end we are going to solve the equation of motion only, right. So, how we do that, that we are going to discuss at the end, and this is the keyword that you can use to find out this lecture. So, now we have actually need to calculate the three different restoring coefficient C33, C44 and C55. Now, since we have not discussed about the JK, remember in my the first lecture we discussed that we have not yet discussed about the use of this J and K. So, let us you can ignore here also, but physically try to understand what is the C33 means. So, what is the C44 means and what is the C55 means. Now, if you look at the 6 modes of motion, which is surge, which is along the horizontal axis, right. We have the surge, which is, now let us draw the ship just for clarity. Now, if you consider the surge which is along the horizontal axis, x direction. Now, this motion or the surge, it does not experience any kind of restoration, right, because there is nothing to pull him back, nothing. Similarly, if it moves along the direction of y, slowly drifting along this axis, so there is nothing, no force which is actually pull him back. Eventually, if you rotate along this vertical about the z axis, that means it just rotate like this way. So, really there is nothing to stop the ship, right. So, now you understand that out of these 6 modes of motion, there are 3 modes of motion where there is no restoration. However, if you consider that ship is actually heaving, that means is going downwards, then there is of course, there is a buoyancy force that is actually pulls him up, right. So, it experience kind of forces. Now, even in case of a roll, now if the ship again, if the ship rolls like it rolls, let us say, let us draw a midship section somehow, and it actually rolls. So, then they experience that a moment that pulls him back. And also if we consider this in direction of very badly anyways, here also, so again it experiences a moment. So, therefore, I understand that there are at least 3 modes of motion where we can have a restoration. Now, in case of a heave, we are using C33 and this is the nomenclature, and in case of a roll we use the C44, and in case of a pitch we are going to use the C55. Okay. So, now in C33, now rho is a constant, g is constant. So, only thing we need to do is how we are going to calculate the water plane area, right. Now, in case of a C44, you can see that now rho g is that how to calculate, I mean the here is a nabla is displacement, right. Remember, this is a typical ship nomenclature or the notation we use this for the volume. Okay. So, then here everything is known to me, and also the GMT is basically the input. So, we have nothing to do with that. I mean we cannot geometrically calculate the GMT, that is what I mean. Now, in case of a C 5 also, now it is again that first 3 term actually and then GML also can be a input, but however, that GML can be approximated by BML and this BML you can calculate numerically. Okay. But now we have to understand, but this is all the hydrostatic things and definitely more detail will be there, but here again we are discussing it because for the sake of completeness. Okay. Okay, fine, fair enough. Now, how we are going to calculate the C33? Now, you know that it is that rho g into water plane area. Now, here I have a nice picture and you can see that that what is actually the water plane area, right. So, as I discussed last class, like if you take a small strip along this axis, right. If you take a small strip here and this is basically your y, right. So, therefore, and if you multiply by the dx, so you can get the area, right. Now, then you just this area if you successively add for each section, right, then actually you can get the water plane area, right. Now, from the offset table how you get it? Now, offset table also very easy, because in offset table, because here it is, you remember that this is basically the design water line and call this as z equal to 0. Remember that when you calculate hydrostatic, normally this last point here, this point is noted, I mean this point is denoted by z equal to 0, right. But in case of hydrodynamics, that what we are doing here, we define this z equal to minus t, where the t is the basically the vertical distance from the water line to the kill point. Kill point is means the bottommost point. So, we define this as 0 to minus t, right. So, there is something that actually you have to understand, like if you are using some software like Wamit, you have to use this convention. However, there are many softwares like even they are using that this orientation, that normally that what are understood from the hydrostatic, they define the z equal to 0 and this equal to plus t, okay. And then they change everything internally. But anyways, remember that here the z is fixed, you call it z equal to 0, you call it z equal to t, does not matter. Idea is this is the topmost point, above there is nothing but the air. So, you take this point and then you calculate. So, now in this table, now I know that the vertical z equal to 0, let us take z equal to 0, and then we have a table for x and y. So, that means at each x location, x I location, we have the y I, right. Then if you plot it, then you can have a graph. So, this graph might be look like this, I mean let us say, and then this basically at some point x I, this is your y I. So, therefore, if you integrate it along this axis, so let us say 0 to L, then y I dx, that can be given, that would be your water plane area or AWP, right. So, this is how actually we are going to get my water plane area, fine. Okay. And then of course, once we get the water plane area, your restoring coefficient is bit easy, it is C33 is nothing but rho g into water plane area, fine. Okay. Now, okay, that is what we had discussed. So, let us go to the next. So, how we calculate the water plane area from the 3-dimensional mesh, right. Now, again as I said, it is very interesting, right. Now, we have to calculate the water plane area with respect to the 3-dimensional mesh. So, now the section lines or offset table is not given to you. So, you do not have the data you do not have the data for these points, right. Of course, you have the data, but you need to do lot of calculation, lot of ifs and but, right. That also you can do, of course, like if from the mesh you try to find out the z that x coordinate and y coordinate where z equal to 0. So, you can write a computer program with list of, now this is called the nodes. So, you can run like just numerically, I am just for sake of just let us say I is equal to 1 to number of node, and then you can make a check that x I mean or you can say the point p I where that z I minus 0 less than epsilon, you can check take the value epsilon equal to 0.001. You can do that, but this is not the way the smart people will do. We have better methods, of course, we are going to discuss this. Well, now suppose you have this mesh with you. Now, what you need to do is, now let us say this is the red thing that you are select this mesh here, right. So, then what you can do is, so you can find out the area, let us say dsi basically the area, okay, right. And if you remember that this area, if you multiply, I mean by the normal n z. So, essentially what you are going to do, basically you are taking the projection along this plane, right. Now, you see what is actually happening. If I show you in 2D, it will be very clear to you. Now, suppose this is your section line, okay. Let us do it for 2D. So, what is your interest? Basically your interest is find out this length, and but you have the information or nodal information of this line, okay. You have the nodal information of this particular line. Now, what you are doing is you take a length and you project in this vertical plane. So, what you get? See, if you take a vertical plane, you are getting this much of length. Again, if you take these 2 points and you take a vertical projection, then you get this much of point length. Now, again if you take these 3 points and if you take a vertical projection, you get this. You keep repeating it, taking the projection in vertical plane, you multiply this length multiply by the normal to the z direction. So, you get it, you get it, you get it, you get it, you get it. So, I missed the first one. If you do this for the, so you can say that just doing it. So, what essentially that since already you have mesh, right, you have the area and you also know what is the normal of this I mean the all different sort of normal. So, why to waste time to calculate all the points actually which is lying on the z equal to 0 with some very badly written not badly, very nicely written also, but it will again computationally expensive and we really do not want. So, normally if you do the meshing in let us say I mean it will, let us say you can have some thousands of nodes. Okay. So, now in thousands of nodes you are going to find out like there is some 10 or 100 of nodes which have this, which occupying this in the free surface here z equal to 0, and then from that you will going to do, it is not very smart way of doing it. However, this one is much straightforward, right, because you have all the data. When you calculate the hydrostatic force, what did you do at the hydrostatic force? You are calculating the minus rho z into the centroid z I into dsi, and then you take the projection n z, right. But now what you need to do is you have the dsi and you take the projection. So, that will give you the some piece of the water plane area. So, therefore, now if you add this A I, then you get your water plane area, right. And now you know that how to find out the normal vector, right. Now, again just repeating, I know that you all know all these things. So, I have this thing. So, you have defined the vector, let us say v 1, and just take this another vector v 2, and then if you make v 1 cross v 2, then definitely you are going to give the normal vector, right. So, just you get the normal vector, multiply by the z component of this vector, you will get the water plane area, right. So, this is how actually we can get the water plane area if the mesh is given to you, right. Okay. Now, let us coming back to that calculation of the C55. I am not going to discuss C44 because the GMT is always is a input. Unless you have this I get the GMT, we can approximate by some numbers of course, but normally it is the input. Okay. Now, let us find out that how I calculate the C55. Now, formula for calculation of the C55, I mean it is basically the how I calculate the BML. It is given I y y by delta. So, you know that I y y how to calculate I y for a different thing. So, I am not going to discuss about this. So, this is the straightforward formula that we are going to use, and then the moment you get this, I actually I have for simplified case, let us take a rectangular barge. So, this I y you know that it is known for you, it is L b cube by 12, everybody knows it. So, that gives you the idea of BML is basically L square by 12 T. Now, why I am writing this, there is a purpose. So, the main purpose basically to give you some kind of rough approximation or estimation that what would be the range of the BML. Now, normally now this sort of idea is very essential for an engineer, like for example, like what should be the ratio between the length of the vessel to draft of the vessel or the beam of the vessel, right. Normally, we can I mean there is a vary, but like L by B, you can make it like 6 or 8 or something like this, or L by T, you can approximate by 10 or something like this. Like this is a thumbnail like that you can use it. Okay. Now, actually having said this, so if you take this, okay, then if you see this L square by 12 T term, then you can understand very well that BML is kind of order of the length, because T L by T you can replace by 10, right. So, or 12 or something like this. So, then you can understand that the range of BML is very close to the L, right. So, this is our take basically, like, so we can say that approximation of the BML that we can make, like we are not going to, let us say we are not even do the calculation to calculate the BML, we do not do that. Okay. So, but we need some values, okay, to get the restoring force C55. We need a very quick calculations. Somehow sometimes we need we do not have much time. So, we have to calculate the motions, we just need to put some number. So, it is essential to get some idea about the numbers, right. So, now this BML we can see that we can approximate it by, let us say 1.1 L or 1.2 L for the quick calculation for C55. Okay. So, let us see that how realistic it is. Okay. remember this formula for BML is L square by 12 T, right. So, now let us do one thing. Let us really now try to calculate the that how this approximation is valid or not. Let us try to find out. So, let us take one rectangular barge. And let us take this length as it is. I just take it is 100, and let us take it is let us take 12, and then let us take this height, it is 10, right. Now, find out what is the BML. So, I know that it is L square by 12 T, right. So, L square is 100 into 100, then it is 12 and it is 10. So, it is 1000 by 12. Now, it is around 70 or 80, something like this, right. So, you can see that the length is L. So, 100 is basically the length, and then it is coming out 80. You can say there is a 20% or something like it is a deviation, but I will tell you that there is a difference between the shifting and the microsurgery, right. Here this 20% is allowed because the moment is very high, and that some I mean there is still some 10% is still in the acceptable range. It really does not matter, right. So, because if you consider the numbers, it is very large. So, therefore, and it is not that sensitive towards these values also, very not. I do not say it is not sensitive, it is not too much sensitive. So, therefore, this first hand approximation actually works nicely, at least for this at least for calculation of this C55 and so. Okay. So, let us move on to our next topic. Okay. Before that, like we talked about the BML, BMT, GML, GMT. So, let us try to find out what is the actually M here, right. Also, again referring to the hydrostatics, everything is given nicely over there. So, I am just sake of completeness I am giving some basic standard definition. Now, here M is known as meta center. Now, what is meta center? If you look at this picture in here, so this is the initial position of the ship was W1 L1, and then it tilted, right. It is tilted in direction of, let us say it is I am taking a cross section, that midship section, I just tilt that midship section. We are now talking about the GMT and the BMT, okay, fine. So, now I just if I tilt here, now you can see that we have new water line WL, right, and also you can see that the buoyancy actually shifted from B to B1. Now, here to calculate there is something like to calculate this meta center, we have a approximation. The approximation about that, the tilting, this angle theta is small, and then how small. Now, when I say the how small it is, we are what I am talking about. If you like I will tell, like if you tilt more, then it shift more. So, therefore, M will come down somewhere, like. So, we can see that M should be the function of theta, but we say no, M is not function of theta, because this M when at the limiting point, when the theta is very small, that time I can calculate the meta center. Now, let us first see how we calculate M. Now, here from the B we assume, this assumption is that the shift of B is only in the horizontal direction. So, if it is B, then it shift only at the. So, normally what happened, it it shift B can be in general it shift horizontally also vertically, but however, we ignore this. Now, if I shift it horizontally and then if you draw a normal to the new water line and the point it meet at the initial normal to the initial water line, that point we call as a theta. Remember that here the shifting takes place only in the horizontal direction. So, this is somehow in case of the large moment, then definitely this m is function of theta, but that time we do not call it meta center. We call meta center when the theta is small, right. And then once we understand the value that m, then definitely we understand that what is B m, which is nothing but the distance from B to m, and then G m is the distance from G to m. G is the center of gravity of the ship, right. So, that means when the mass distribution is given, you know the value of G, and therefore, you know all the value of B m, G m, etcetera, right. So, here similar thing actually similar thing basically in case of a GML and BML also, right. The concept is same, that only thing is that instead of tilting in this location, we tilting in this direction to find out that meta center for that GML and BML. Okay, now let us come to the final part of it. Let us now, you know that we have the equation of motion, how to solve it, right. Now, let us discuss a very easy scheme, that is Euler scheme. Let us see what is this Euler scheme. Now, we are going to solve this differential equation du dt equal to f t, and what is given is the du dt at initial time t 0, value of du dt and then value of the u at the initial time, right. Now, what we are going to do here, like everybody know, is basically we are doing the straight line approximation. So, you can see from this graph, it is at t 0 it is here, and then at t 0 plus delta t it is here, right, and then we just join this as a straight line. Now, you can see here I am writing that equation of this straight line, right, which is u t minus u 0. So, we know that the equation of straight line y minus y 0 is equal to we can say du dt or let us say du dt into t minus t 0. I am just doing it, right. Instead of t, I am writing t 0 plus delta t, that is the only thing I did, right. So, it is u t minus u 0 equal to the du dt of course into dt, because here t 0 cancelled out. Now, here I just would like to discuss one small thing in 1 or 2 minutes, not. So, this is the slope defines if your method is implicit or explicit. If you are doing du 0 by dt, that means you have to consider a slope at this point, it is the explicit method, but instead if you consider slope at the point b, then it is the implicit method. Then what is explicit method, what is implicit method? Definitely you have several courses for this. So, I am not going to discuss elaborately, I am just discussing here as much as required by me for this particular course. Okay. So, now here this is my final equation, numerical equation. So, I try to find out the value of u in future time step dt if I know my value at the present time as well as the du dt at the present time. So, how I am going to use this for my particular case? Now, here we are going to solve a m x double dot equal to f. So, now I convert this into the first order equation, which is v dot equal to f by m. So, x double dot is nothing but the velocity dot, right. Now, I am using this Euler approximation scheme. So, I can find out the velocity at the next time steps equal to velocity at the present time state plus the functional value, right. So, the moment I get the velocity, again I can use, because I am going to use basically again that x dot equal to v, right. So, that means that dx dt equal to v. So, if I use this, so definitely I can find out the displacement at the next time step if I know the displacement at the present time step. Also, now here I can make an improvement. I am using, since I have already found out the velocity at the next time step. So, I am using the velocity of the next time step. Now, you see that this scheme we can call as the explicit, and here you can call is the implicit, because here I am using to calculate the velocity the slope at the present time, here to calculate the displacement I am using the slope at the present time steps. Okay. So, actually this is all about today. So, from the next class onwards we are going to discuss about the modes, the J k, and actually how we are going to apply this method in numerical ship hydrodynamics. Definitely we are going to discuss from the next class. Okay. So, till then thank you.